this is a pretty nice video that you can actually say is whatever we talked about. There is, if you look at the video very closely, there is deformation, there will be what we call shear stripping, and then there will be the ligaments that he already talked about, and then you get all the hell actually breaks loose, right? So, and because all the hell actually breaks loose, atomization is a very tough problem to tackle with, because we have not figured out turbulence, and this is like one level above that. So, okay, so this will be the broad kind of an outline. So the introduction and motivation, well, all of you know, kind of. And then there will be some interesting experimental configurations to study secondary atomization, because primary atomization, Marco and I think Professor Tropia, they all talked about. So secondary atomization also people have worked for eternity, okay? And there are certain interesting setups that you can actually do. And then of course, there are some non-dimensionalization that we do, and there are certain atomization modes that we will talk about out of that: vibrational, bag, shear, multimodal, and catastrophic. The last one is rather interesting because it's called catastrophic. That means we don't know what the hell it is all about. Okay, and there of course opens up a little bit of opportunity to do quality research in all of them, okay, except maybe vibrational one. And then we'll talk a little bit about droplet breakup time scales and how the modes actually interact with each other, and so long and so forth. Okay, so that's good. This sets the stage for the introduction and the motivation part. Well, gas turbine engines is there. As we know, at the heart of the gas turbine is a combustor. Combustor uses sprays. The sprays, why the sprays are important? Because breakup of the sprays introduces the mist, which ultimately leads to mixing, and ultimately leads to what we call combustion stability and efficiency, right? So it adds that extra time scale of mixing, okay, in the whole mix of things, okay? Then of course there is thermal coating out of that SPPS, that is called actually solution precursor plasma spray process. So these are all used for creating this coating on gas turbine materials and stuff like that. Of course there is pharmaceutics as well. That means how you make drugs, powders, and milk industry. This everything comes under sprays. Sprays are there everywhere, okay, including the coughs and other things that comes out of our mouth. That is also sprays. Okay, so relevant even to COVID. So we already talked about primary atomization. So primary atomization does the initial job. It breaks things up for you a little bit, right? Either it is inside the nozzle or inside and outside the nozzle, both, okay? So after the primary atomization, if you look at it here, you start getting these daughter droplets, right? So these daughter droplets now break up into even smaller daughter droplets, and that is secondary atomization in a nutshell. So primary atomization will do this. Secondary atomization will take care of the rest. So it's like a mop up, right? You mop up the entire crime scene, so to say. So understanding why this is important, because if you understand the secondary atomization part, secondary atomization basically allows you to do a few things. First is that to produce the ultimate droplet size distribution, right, before it enters into whatever, right? That the second part is the dispersion. Because these are small droplets and they are carried by the flow, right? So how they accumulate, how they spontaneously display heterogeneity or homogeneity, right, depends on what is the daughter droplet sizes that you are actually producing, right? So the dispersion is one aspect. That means how well these are dispersed actually enables you to do whatever that you are trying to achieve, right? And as you know, the flows are notoriously complex, as had been said earlier, that when you have swirling flows, when you have shear driven flows and flows like that, they are never uniform. So they have strong vorticity gradients, right? And because of that, the dispersion of the droplets are affected. Okay, so what we are not talking about today, and maybe we can talk about later, is that moment this dispersion characteristics changes, the droplet heat and mass transfer also changes. And that actually changes what we call the mixing of the droplet. That is the mixing of the vapor phase. All right. So how do you study there is secondary atomization. Okay, there are three ways. Okay, three common ways. Okay, and there is one or two uncommon ways also by which you can actually do the same. Okay, the first one is the shock tube. That means you have a droplet and you have a shock. So it's like hitting the droplet with a high velocity gradient. It's like a sharp velocity gradient, right, from 0 to whatever value. Okay, that is what happens. As you would see over there, the shock does not do anything. It is the flow behind the shock that does all the damage. The shock passes over the droplet and the droplet doesn't feel a thing, right? It's too fast, right? The second one is the most commonly used one, where you have a nozzle and you drop the droplet, right? Either in this configuration, it's like a transverse injection, or you can inject it with the droplet line also, right? So this is like it sees a sharp velocity gradient as it penetrates through the shear layer, and then it encounters a uniformish kind of a flow. So that is what is there in the middle, right here. It encounters a uniform kind of a flow, right? Okay. The third one is basically a drop tower. Basically, you drop the droplet from the height. What happens is that as it passes through the atmosphere or through the drop tower, it continuously accelerates. So it's like a raindrop kind of a model. So people who wants to study the raindrop atomization and stuff like that, they use a drop tower, right? Each has got its own advantages and disadvantages, right? Because shock means that there is a sudden velocity gradient, okay, which is sometimes hard to find in real applications, right? Continuous flow has the problem is that because the droplet is passing through a shear layer from a zero ambient kind of a flow to all of a sudden the high speed flow, if the droplet has a low surface tension, as we talked about, it will just break up before even it gets into the uniform flow section. So the idea is that the breakup time of the droplet has to be sufficiently long than the entrainment time, right? Sometimes that is not very easy to maintain, especially when you are dealing with, fuels which has got very low surface tension. All right. The drop tower is the best in a way because it allows you to have the full blown, the droplet nice and easy, okay, but it requires, as you can see, is a substantial height problem that you will have. All right. But each allows us to introspect a certain amount of the phenomena at hand. There is a fourth one, okay. You can even use a levitator for this, provided you perturb it well enough, okay, because all you see that there is a relative effect. So if you levitate something and then you perturb it, if your perturbation is strong enough, there also you can study what is going to happen to the droplet. A little bit unconventional, but perhaps doable. All right. So normal, there are varieties of ways in which you can do the shock tube experiments, for example. So this is a normal shock tube. All of you know there is a driver section, driven section. You pressurize it enough, burst the diaphragm, the shock propagates. You have a section over here, where you basically monitor what is going to happen to the droplet. It's at max a millisecond phenomena. You can have very high speed diagnostics that are available these days. You can take breathtaking pictures, right? Only problem with this particular thing is that it has got a very limited operational range, and you know how long it takes for a shock tube. You put the diaphragm back, load it, ram it once again. So each experiment takes a little bit of time. So what we did, and this Professor Tropia knows, we have a portable shock tube. This is in my lab, where we use basically an exploding wire technique to generate the same shock. This is portable, roughly about this size from the base, right? What this enables us to do is basically you now can use different contraptions to focus the shock on anything, right? And this can be shock on demand. This has got a very fast turnaround time. So as you can see, we can pass it through a levitator with a droplet hanging there, and you can see the breakup modes rather clearly, okay? So that is a possibility. So here is an exploding wire right here. So it vaporizes the wire, so it creates a blast. And then you use contraptions to make it like a more of a planar shock. Okay. So that is what we did. And, okay, we will show some pictures of that in a little bit. Okay, this experimental configuration is also from our lab, where basically it's a very standard thing. You have a large plenum, you have a jet which comes nicely, it's a conditioned flow, and then you have the droplet which basically passes through this shear layer and gets entry into the jet. Okay, and here of course we already heard, not going to repeat the parameters, the Weber number becomes a very important part. The Weber number is also important in all the cases, but one should have a little bit of, you use the concept of Weber number a little bit, responsibly. It is not just the aerodynamic forces, in most cases it is. Okay, in cases, especially with applications which involves turbulence, it can also involve the circulation based Weber number. That means, for example, this is a droplet, especially in secondary atomization, you will find that there is a vortex which rolls it up. Okay, so the main flow is rather, by Weber number, we naturally mean the inertial forces which are rather nice. But if you have a vortex which is squeezing the whole thing, then it is a vortex based Weber number, or basically a fluctuating Weber number, which becomes rather important. All it means is that there has to be some kind of an inertial effect. It could be a pressure difference, it could be an aerodynamic force, it could be vorticity, it could be any other thing, divided by whatever is a restoring function. In this case, of course, the restoring function is always surface tension. All right. In fact, I will mention one other instability as I go, right? Because, one other thing, just for making things a little bit light, you will always see the name of Rayleigh everywhere. Rayleigh Taylor, everywhere somehow. So fluid mechanics instabilities have ended with these guys. Kind of, no new instabilities are found. Anyway, so this is what it is. And here, of course, as I said earlier, the key parameter is that the droplet velocity before it enters the stream has to be sufficiently lower than the critical Weber number of breakup, and the shear layer has to be thin enough so that the droplet passes through the whole thing without getting atomized, right? Okay, so these are the two things that you should keep in mind. And then this is the drop tower facility. We also have this. Okay, this is what Khushbu worked on. So drop tower facility, of course, this is used for combustion and other things. This is gradual acceleration as we talked about. So some of the things like Rayleigh-Taylor instability will become prominent over here because it's accelerating framework now. Used in atmospheric studies, also used in combustors simulations, microgravities, a lot of stuff. Okay, so these are the 3 or 4 different models that you will have. Okay, now if you want to characterize secondary atomization, honestly speaking, before the story becomes complicated, first one is a deformation. The droplet will deform. This will happen in all the cases that you see. It's not like that all of a sudden something is going to come out of you. You have to get deformed. Okay, so first one is a deformation phase. So what happens is that if there is a flow, the droplet from being a sphere will become an obloid type of a shape or ellipsoidal shape in this direction. Naturally, what it will do is that it will create a substantial wake, as you can see over there. There's a wake part near the rear stagnation point. Result of that, there will be substantial pressure difference, and this is a non-recoverable process with respect to that. So if the droplet had very low surface tension, it will immediately become a pancake. It's only the surface tension that tries to pull it back, right? Because the wake, more flatter it gets, the wake becomes that is normally you cannot recover that configuration back anymore, right? So that is the first thing. Yes. It's a pizza. That's true. That's a pizza with 60% of the mass in the rim. Right. So the second phase is that once the stage is set, that the droplet is deformed, now you bring out all your machine guns into the picture. So first one is the most easiest part. That is nice and lit. Vibrational mode of breakup. Right. It's basically a dancing sequence. You dance and then you break. That's what happens. And it depends on the natural frequency and a lot of other stuff. Then comes a bag. Bag is nothing like a balloon. You will see a balloon, and if you inflate the balloon, there is a rim which Professor Tropia was talking about, and then there is a balloon. As you go on blowing the balloon, the rim becomes thinner and thinner and thinner and thinner, and ultimately you get these holes. Why the hole forms, that's a different story. Okay, it's very difficult to understand that. So the bag breaks, and then the rim breaks. Okay, the rim also breaks. Then there can be a case where you have multimodal breakup. That means it inflates, but there is a stamen. So it inflates like this. There is a stamen, which is exactly what is shown over here. This is like the stamen. Okay, and then it breaks in a very similar way. Then you have the case of shear thinning. That means you have this droplet like a rim now, and at the edge there is a little bit of a sheet that comes out. Now that starts spurting out. Okay, so that is kind of a shear thinning. And the last one, about which I am kind of totally dumbfounded, is basically the catastrophic, which means, as Professor Marengo said, there's a whole gamut of breakup, okay, contributing in a spectacular way. Other way of saying this, that I don't know. Okay, so I don't know why it happens, how it happens. And remember, all the stability analyses that we talk about, and we still do, they are all linear stability analysis. That means the modes don't talk with each other. That's why you have one singleton mode, and then you say that is the most dangerous wavelength, everything else is kind of garbage and stuff like that. It's actually not that. It's a nonlinear process. So you have all kinds of harmonics which gets populated. All right. That is the difficulty, how these modes actually crosstalk with each other. Okay, is something that is mathematically pretty onerous. You have to ask an applied mathematician, which I am not. Okay. Okay, great. So if we now start to look at the droplet deformation phase, okay, as it is already said that the aerodynamic drag is very important. That is the force. Okay. Once you try to determine the aerodynamic drag, you know it scales as square of the velocity, which is easy. But it also scales as the frontal diameter, which is also a frontal area, which is also easy. CD is one part that we are not sure. That is the coefficient of drag, right? Okay, that is the drag coefficient. Now, whatever things that you see over here, this is, for example, a relation, because it seems to scale with Weber number and Onsorge number. Once again, this particular thing absolutely has no physical basis, right? It's just a curve fit. It's just a regression analysis where we have collected a whole lot of data and have fitted a curve, and this seems to be working the best. Okay, all right. So here, of course, you will see that there is a Weber number dependence, and then there is a Onsorge number dependence over here. So Weber number, as we said, is basically how you want to destroy the whole thing. So if you go down in Weber number, your drag will approach kind of 1.6. Okay, if you go on increasing the Weber number, it becomes a slightly higher value. Onsorge number is, however, viscous force and surface tension force is typically a little bit of a late acting force. Okay, so if you try to open up the time scale for the whole thing, you will find that the Onsorge number effect, which is basically nothing but a damping effect, will come a little later. All right. This will come a little bit of a later, and that will be evident if I show the next plot over here. Okay. Why am I? Okay. So let's see the different videos. These are all nice watching. You see a bag and stamen breakup. This comes from our shock tube experience, and then on the left hand side you see the bag breakup. Okay, so you can see whatever I have said, we are showing it. Okay, so seeing is believing, so look at it very carefully. Okay, don't question me later. And this is, for example, the sheet thinning. You will see it a little later. See that? You saw the sheet thinning. And the right hand side, which is the catastrophic breakup. If you look at the catastrophic breakup a little closely, you will see something interesting. Initial part resembles this kind of sheet thinning, and then things gets a whole lot complicated. So you see, initially everybody is simple like us, right? Then as we grow old, we become more complicated. It's very similar to these pieces over here, right? Oh, I don't know if that was a good statement or not, but anyway. So, a quick word about so I have provided evidence what happens. Vibrational mode of breakup is something that you can even do at your home. I think that is not a useful example to show. The non-dimensional groups, we have mentioned 3. These are already well characterized. Onsorge number, little late acting, little laid back essentially, then Weber number and Reynolds number. There are actually not 3, you can combine them into 2, okay? But there is 2 other dimensions that are there. One is a Mach number effect, because when you have compressibility coming into the picture, it is there, which is normally not used that much, okay? And the other one is a little bit more interesting, because Onsorge number looks into the viscosity. That means highly viscous fluid, like honey, for example, or you want to do slurry fuel or whatever, I mean. But if the fluid is a little bit complex, that means if there is an elasticity attached with the fluid, right? That's not the same as viscosity. When basically you have shear thinning and other kind of behavior, okay, you have the elasticity number also that should come into the picture, okay? So things are not as rosy as it seems to be, right? But that's how things are. And of course, there are the density ratios and the viscosity ratios, everything else, okay, that comes into the picture. Great. This is the most important map that you can think of, and this was done in 1995 by Jerry Faith, most likely. Okay, and what it does is that if you look at the map very carefully, you will find that why I said that Onsorge number is a little laid back, right? So you see, for a large range of Onsorge number, remember the log-log scale, it actually changes by 3 orders, 10 to the power of -4 to 10 to the power of -1. Do you see that? With increase in Weber number, Onsorge number doesn't have any effect at all, right? It's kind of flat, right? Whatever is the Onsorge number, the Weber number, it determines the mode of breakup. So these are the different modes of breakup. So shear breakup happens always at Weber number, which is greater than 100, right? Or 8-ish actually. Then you have the multimode breakup, this bag, oscillatory, deformation. All of them you see, it somehow is independent of Onsorge number. Whatever is the Onsorge number, I will exhibit these characteristics. That's why you could come to this particular map. For Onsorge number less than about 0.1, you see that the vibrational, bag, multimodal, all these things that I described was only a function of Weber number, right? That's why I said it's a little laid back, okay? Things starts to get a little, interesting, intriguing rather, as you go on in this higher Onsorge number range, which is one way of saying higher viscosity fluids, right? Or high pressure sprays, both, okay? In these cases, what happens is, look at how the curve actually turns up, okay? And as the Onsorge number increases, the curve slope actually changes rather drastically. You can see this is on a log scale, so you can see how steep the curve can be. So that means if you are at an Onsorge number of say 1, right, okay, your modes of breakup will typically require much higher Weber number. That means if you want to go now to the shear breakup mode, your Weber number has to be like 3 or 4 times higher than what you are normally encountered with, right? If it happens at 100, it will happen at 300. That means you require higher aerodynamic forces, or in other words, you need higher velocities. Simply, if you higher velocities, higher pressure, higher vorticity. It has to be high, 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 right? Because of that. And as you go further, if you make it very viscous, right, you can see in some cases, some modes are completely suppressed. And we have evidence of that. When we actually did our experiments with polymeric fluids, we actually saw this evidence that some of these modes were completely suppressed. Okay. So the idea is Onsorge number effect starts to become more and more dominant as you go on to higher and higher values of viscosity. Typical slurry fuels or viscous fuels will have that characteristics. But the idea is this opens up one important research question over here, if you guys are interested in that, is that is there an universal map that you can come up with Weber number and Onsorge number in this regime? It's not yet done, and hence an open-ended question. And remember, complex fluid has not even come into the picture. This is just high viscosity fluid, which has got only one value of the viscosity. All right. So this is an important question you might want to address at some later point in your career. You can make a name for yourself. Okay. So now let's look at each of the modes of breakup. Okay. And for the purpose of pedagogy and others, first one is, of course, the traditional vibrational mode. This typically will produce droplets which are order of its own diameter. So if you start with a big droplet, you basically, generate offsprings which are half of that size, right? But they are still going to be large. If the droplet is large, your offsprings are also going to be large. And this is typically modeled by what we call the Taylor analogy breakup model, or the TAB model in short. It's basically a spring mass system with K being the surface tension and mu being the damping factor. Okay, so surface tension restoring, and that is the damping. All right, and that's why you will see that damping has got a U attached with it. Okay, so unlike a deformation, damping requires a velocity. Understood? Like the spring, if you squeeze the spring, okay, it's the degree of compression that actually determines how much will be the restoring force. That case, it requires a velocity with which you are pushing. Okay, so it is like a dashpot type of a system, and these are relationships once again that you can produce by doing just an energy balance of the whole thing, daughter versus the mother droplets, and this is what you get. Typically, these modes of breakup are available at Weber number to less than about 4. So at Weber number greater than 1 means you just have enough inertia to push things out of bounds, and 4 means that you are relatively in the lower aerodynamic or inertial range. Got it? Okay, now this is the bag mode of breakup. As you can see, you create a forward stagnation point where you have a very high pressure, right? The flow curves around it. So it is first a deformation in an oblate spheroid, and then you actually have formed this cup like this, essentially like this cup, and as Professor Tropia said, with a rim. Okay, and that is what happens at below what you saw the video. That is how it actually breaks up. So the membrane actually breaks up. Okay, and then the toroidal ring breaks up. Okay, now this gives rise to the other question that it is basically a pressure differential effect, right, as you can see over there. And of course, as it grows, as Professor Marengo also said, the sheet becomes very thin and you have got perforated holes. The hole that you see over here, this is a hole. Okay, very nice hole, right? Now, why this hole is created, okay, is almost impossible to model unless you go down now to the van der Waals and stuff like that, right? Now, there are several theories attached with it, why the hole actually forms, because it's not a simple capillary instability like the Rayleigh plateau and others that we are talking about. It's a little bit different, right? So it's like a sheet which is continuously thinned and thinned and thinned, and then it develops the hole. So it could be, in effect, when the sheet is small enough that the local perturbations in the flow field would be having an effect. So local perturbations, I mean, if you look at a turbulence spectrum, you go down to just into the Taylor microscale type of thing, Kolmogorov scale up. So there you see where the eddy sizes now start to match the sheet size, right? So there, that's why I drew all these nice little eddies over there. They would be doing this popping mechanism, and these eddies are always present in any realistic flow field to begin with. You can't avoid it. That could be one. The other thing could be any impurities, like you actually have bubble formation due to nucleation mechanism. There could be also impurities which could be leading to this kind of fractures. These are like little fractures, and then they grow. So they can be pulled back also, but in this case they will grow and they will lead to the bag getting atomized. This is a little bit of a different mechanism which cannot be reconciled within Rayleigh-Taylor or any other capillary instabilities. Okay. Again, an open-ended question that you should kind of try to address, okay, if given the chance. All right. So, so the bag, if you look at the bag, it breaks up into ligaments in the direction of the flow. Do you see that? It in the direction of the flow. So so that's the reason, because these holes are developing in a perpendicular direction of the flow, basically. So that's the reason why the perturbation theory is there. And then the rim, which is this part, okay, that contains a lot of fluid, by the way, almost 60%, because the rim is, the bag is rather thin. So you can see, even though it has a large, large radius, is the thickness T is rather small. The rim carries a lot of this. So the rim basically gives rise to these rather big sized droplets, whereas a bag, because it's a bag, it gives rise to fine mist. Now what happens is that these droplets can further undergo the same process, again doing the same thing. It's a cycle that continues till the flow is conducive enough. All right. So it's a cascade, so to say. Okay. Now there can be different, growth profiles or different time scales that you can advocate. Okay. Again, these comes from, different experiments. Some includes ours. So the time scale is typically normalized by something. Is usually, sometimes can be the capillary time scale, sometimes can be the residence time. There can be many types of things. These are all data that you should take with a pinch of salt, because some of them, these are not regulated enough. They are not universal enough, okay, which includes our own data. But still, it goes without saying that, the time scales, the exact values. Once again, you should get it in your mind that notionally what happens. First, there is a deformation, then there is this breakup, or this extreme deformation phases, and then you get the breakup, right? So there is a segregation of time. So you can understand this time will be short, this time will come after that, and that time will be the longest. But exact values of these times are still something that is still debated, because there may not be any universal time scale at all that actually exists. And still it is a hot topic for research. Okay. Then comes the shear thinning. Okay. Again, look at the video carefully. You saw that little thing coming out. So it is called, essentially explained by two mechanisms. One is basically the boundary layer stripping description, and the other one is a shear thinning description. We are just going to go through each one of them. So what happens is that when you have a flow around the droplet, you develop a boundary layer in the gas phase and in the liquid phase, and you have an interface matching condition. At the interface, the velocity should be the same no matter which direction you are coming from, but the gradient will be different, right? Because you have to match the shear also at the interface. So the gradient will be different because the viscosity is different, etc., right? So what happens is that due to this, okay, the boundary layer inside the droplet becomes unstable, right? And that leads to this kind of a stripping. That is the stripping mechanism. Right. This is supported by some of the arguments that the droplet viscosity was found to increase the ligament sizes. It is experimentally observed. Okay. All right. So that is one such condition, that now also the increased diameter of the daughter droplets is based on the temporal growth of this boundary layer. Okay. So this requires treatment, which you can do simple with a pen and paper kind of an approach, and you can still come up with this hypothesis. The other one is is a shear thinning kind of a mode. In this, what you do is that you neglect everything that happens within the droplet. That means there is no internal recirculation, the pressure gradient. It's basically an integral approach. So you integrate everything out, right? And then you predict forces like this. Okay. But this model had got one caveat, that it predicted that the viscous forces increase with decreasing Weber number and increasing Onsorge number. Experimentally, you don't see this. Now, the fancy part of anything, that any theory that you do, if it does not match with experiments, you have to throw it out. As simple as that. That's a rule of thumb, right? No matter how fancy it looks. So these are once again what we call relatively reduced order understanding of what is going on inside. This is, we know the mechanism by which it strips. Now we are trying to explain why it strips, right, by doing this interface matching. Okay. Then of course this was revised in a 1997 paper, right, where it actually says that this is an interesting concept. For all practical values of Reynolds number that you get, okay, the flow is always separate. So there should not be any Reynolds number effect at all. That is the argument. That beyond a certain Reynolds number, the wake is the same. The wake structure is the same, right? So there is a very strong vorticity around the droplet back, okay, but the basic mechanism is still the same. There is this shear, okay, but you understand what I am trying to say. Beyond a certain Reynolds number, everything is the same, right? Because you are in a zone where it doesn't matter, because the flow topography essentially looks the same. Okay, so it just strips away in the same way that you do at Reynolds number x versus x2, right? So that is the thing. Okay, so all these theories have got certain experimental validation which works, and in certain cases it doesn't work. All right, so, and these are some of the details that how the droplet actually breaks up. These are all kind of just numbers. You can just go through the math and you can come up with these numbers. These are nothing spectacular. I mean, these are pen and paper calculations most of the time. Okay, but the transition from bag breakup to shear thinning breakup, okay, that happens for low Onsorge number. We are talking about 0.1, because there we saw Onsorge number doesn't play a major role. So there the back stamen breakup happens between Weber number 18 to 40, and stamen and sheet breakup starts to happen after 40 to about 80. These are once again rough numbers. Because they are Onsorge number independent, that means any type of fluid should be universal, so long and so forth. So these are the two corresponding videos which basically shows the same thing, the bag and stamen and the sheet kind of a breakup. Okay, what you saw, that was just the shock. Okay, so forget the shock. Now comes the last one, or the last but one. This is the multimodal breakup. So this is an interesting mix once again. There are always two such theories attached with it. One is a Rayleigh-Taylor theory, right? And you have a Rayleigh-Taylor and then you have a Kelvin-Helmholtz sitting on the top of each other. So it goes like this. So the droplet, as it kind of accelerates, it's a high density fluid accelerating in a low density fluid, you create perturbations, and then the Kelvin-Helmholtz dances on the top of those perturbations. So it's like dances on a stage that is prepared by this, okay, with a little bit of a phase lag between the two. Okay, dances on the dance. So it's like the gravity kind of a phenomena. You dance on a curvilinear kind of a space. Okay, so this is once again the Rayleigh-Taylor, as Marco already said, that this depends on the acceleration. More is the acceleration, more is the instability, right? It can be gravitational acceleration, it can be any kind of acceleration. So the most, dangerous wavelength is given by this. Okay, once again, it's a single mode analysis. Remember, once again, it's a single mode analysis. And as you saw, that it is dependent on A, which is the droplet acceleration. That means more is the acceleration. Okay, smaller is the wavelength. Okay, so a small droplet accelerating fast enough will have very fine Rayleigh-Taylor waves, while a droplet which is large and kind of moves a little slowly, it will have a slightly longer wavelength. Okay, and the surface tension always, as you can see, if the surface tension is more, the wavelength is more. It stretches out. It just kind of unfurls the wrinkle. That means you are dealing with the same acceleration for two fluids with a small and a high surface tension. The high surface tension fluid will, unwrap the wrinkle pretty fast, make it a little larger. All right, that is what is going to happen. Okay, there is, of course, so this is on a flattened droplet like this, what you saw over here, and this is the wavelength that develops on the top of it. That's exactly what it does. This is basically the wavelengths that develop. This ultimately leads to the stamen and the bag kind of a framework, okay? And he gave this distinction that when they are of the order, the same order, that is the wavelength and this deformed, diameter of the droplet, when they are of the order 1, it implies it's bag. When it is greater than 1, then it implies a bag and stamen. That means there will be like 2 bags, so to say, okay, with a separator in between, okay. This also nicely agrees with whatever we saw. Well, not exactly agrees, but in principle what we saw in our experiments as well. Not exactly, but it's very similar, okay. Another thing, another type of breakup, which I will talk at the extreme end after we cover. The other mechanism is, and this is once again from our work, okay, where we call it's an internal flow mechanism. So when you actually have this deformed droplet, you have a flow from the pole to the equator, like this, exactly the way that is just shown over there. As a result of that, because of the flow, there is a squeezing out, okay, and that leads to the formation of the thin film and all the fingers and everything. All right, okay. So that is also another mechanism that is typically used to explain some of this phenomena. So in summary, the bag breakup, the surface tension is sufficient to resist the internal flow in the case of a bag breakup and resulting in the formation of this toroidal rim. In the case of shear thinning, what we are saying, the surface tension is not sufficient, is insufficient, and the droplet continuously elongates because you have a continuous flow. So there is no recovery mechanism, okay. And in the case of multimodal breakup, the pressure differential across the drop that causes the bag and this rapid deformation, which is responsible for the sheet, both becomes comparable, and therefore you have the dominance of both the mechanisms happening. Understood? So it's how the surface tension is toggled in either of the directions. All right, okay. The other breakup mechanism, which is not covered here, which is something that comes from a combustion literature, and it's still not quite so dominant in the fluid mechanics or in the droplet community, is something what we call a Darius-Landau instability. Now, what is a Darius-Landau instability? It's typically encountered in flame. When a flame actually propagates, it develops wrinkles and it is unconditionally unstable. The wrinkles develop, the wrinkles will become more wrinklish, and it will the flame is going to be torn apart. It will develop what we call holes, which are called the flame holes, extinction pockets. If a liquid sheet quickly accelerates, okay, it's a sheet, remember it's a sheet. If it quickly accelerates, okay, apart from the Rayleigh-Taylor instability, it is supposed to also show Darius-Landau instability as well. But in the case of a flame, unlike a flame, here you still have the surface tension to block the formation of the holes. But that could be one other mechanism, which I did not say in that particular case, could be also responsible for the formation of what we call holes in a liquid sheet, okay, because it's a density. Once again, it's a density ratio driven instability, the Darius-Landau. Founded by Landau means that Landau, okay, the famous Landau, okay. So the last one, and but not the least, it's called the catastrophic breakup. Once again, the picture is here, okay, and from the picture you cannot make out anything. Not my fault, it's the fault of the instability. So what happens is that it's a strange cross-talking now between the RT waves and the KH waves, okay. So what happens is that RT waves it develops in the forward and the rear stagnation points, and the Kelvin-Helmholtz waves elsewhere, okay. Now, what is most important over here, once again, I want to emphasize this, we also saw in our experiments, for a large part of the measurements, you can still describe these two mechanisms by conventional means, RT, Kelvin-Helmholtz, okay. It's only after the topography or the topology of the breakup that you cannot do anything about it. It's very stochastic and it gets very random, just because of the nonlinearity of the process, I should say, okay. So the way forward for this type of work, because computationally you will produce almost the same type of picture, Experimentally also you will produce the same type of picture without understanding exactly what is causing what. It is almost impossible, right? I don't know how many will agree, but I think our math is still poor enough that not to describe that. So here lies, to give a little bit of a spin to the proceedings that are happening so far, you can use the modern generation tools like artificial intelligence and machine learning to bucket it. See, there is a breakup. There's these fantastic structures that you saw and you don't know the hell how those structures are. You can bucket it. You can develop, you can use the what we call physics induced neural network models basically to teach that with Weber number, Onsorge number, whatever number you can pump in here, how you can bucket and produce the data, right? At least that will serve some purpose rather than watching it, oh, this is fantastically beautiful, we don't know anything about it, right? That's what happens. The other part is to measure the diameter of whatever the dotted droplets are coming out. That is the effort that Jatin and Professor Tropia and our lab is actually doing to measure some of these droplets that are coming out of these kind of situations, which are extraordinarily short-lived. Yes, PDPA is very nice. You park it one and then you have a very nicely behaved spray and you measure it for eternity and then you get beautiful distributions. Not from these. These are catastrophic events and it lasts for a few milliseconds. Okay. If you can measure, and there is coalescence probability, a lot of things that happens over there. So using those data, okay, using something like the depth from defocus type of techniques, you measure the droplet sizes from these data with your imaging, with quantitative imaging, even with X-rays and other kind of stuff, you can get high quality data on the catastrophic breakup modes. And we understand what led to those breakup modes. The Kelvin-Helmholtz RT, I have given you one more, Darius-Landau, right? Combining these two, maybe with the help of your neural network models, you can come up with better solutions to your more practical problems. It doesn't solve the physics, but it at least helps you in developing predictive things, right? Do you accept that? It at least is maybe not everything, but it's something to play around with till we are at that stage. All right, I will drop this, and this is a little bit discussion on the droplet time scale that it actually requires. As you can see, this part of the literature is full of correlations. I can make one, everybody can make one, you can make one, okay? Doesn't make the situation any different. It measures the time scale and proposes something. Again, it's simple. The time that it takes for the droplet to deform and break. That's it. It's the sum total of the two time scale. And the time scale it takes for an instability to grow. And then, but remember here, time and space are kind of related because you have an accelerating kind of a thing. So more time it takes, more distance it covers. That's why you saw that thing coming out of the pipe. Okay, it starts developing disturbances a little later because that is the time that it takes to go that particular distance, right? And that's why the penetration happens before you start getting those mushroomy type features. All right, so that's it. I think these are some of the references. Some of them are our papers. Some of them are your paper and whoever else you can think of, right? Okay, thank you.